In 1969, the astronauts of Apollo 11 reported something strange. When they closed their eyes during the long coast to the moon, they saw flashes of light. Bright streaks. Tiny stars that should not exist behind their eyelids. They were not hallucinating, they were not exhausted. They were watching cosmic rays, individual high-energy particles from distant supernova explosions, passing through their retinas at nearly the speed of light. Each flash was a single subatomic bullet tearing through the soft tissue of their eyes, leaving a trail of damage so small that no human had ever sensed it before. And they kept coming. Sometimes one a minute, sometimes more. For days. The astronauts could not turn them off. They could not shield themselves. They could not stop the universe from passing through their bodies. They simply lay in the dark and watched the cosmos pierce them. That was 250,000 mi from home, barely outside Earth's protective shell. And the farther humans go, the worse it gets. Not linearly worse, exponentially worse, catastrophically worse. The universe is not neutral about our presence. The deeper we travel into it, the more aggressively it pushes back. Tonight we are going to explore why space travel is not just hard but actively hostile, why every kilometer farther from Earth multiplies the risk in ways most people never consider, and why the dream of casual interplanetary travel runs into walls that physics itself constructed billions of years before we existed. If you enjoy these deep explorations into the realities of the cosmos, take a moment to like this video and subscribe to Hidden Beyond Stars. It genuinely helps us continue making these journeys for you. Now let us begin. There is a popular image of space that comes from science fiction. Sleek ships gliding between stars, crews waking from cryogenic sleep ready for adventure. A vacuum that is empty, neutral, waiting for us to cross it. That image is a lie, not a small lie, a foundational lie. Space is not empty. Space is not neutral. Space is filled with things that want to kill you. And the deeper you go, the more of them there are, the more powerful they become, and the fewer ways you have of escaping them. Let us start where every human space mission begins. In low Earth orbit, the only place humans have ever lived for extended periods beyond the atmosphere. The International Space Station orbits at an altitude of approximately 400 kilometers. That sounds far. It is not. If you could drive straight up at highway speed, you would reach the station in about 4 hours. Closer than most people live to the nearest major city. And yet, even at this trivial distance, the human body begins to fail. Within days, astronauts experience what is called space adaptation syndrome. Their inner ear sends conflicting signals to their brain. They become nauseated, disoriented, dizzy. Their faces puff up as bodily fluids redistribute toward the head, with no gravity to pull them downward. Their legs become thinner. Their hearts begin to atrophy because they no longer need to pump blood against gravity. Within weeks, they begin losing bone density at a rate of approximately 1 to 2% per month. For comparison, a postmenopausal woman on Earth loses bone at a rate of about 1 to 2% per year. Astronauts lose in a month what an elderly woman loses in a year. Their muscles waste away. Their eyesight changes as the shape of their eyeballs deforms under the altered pressure. Some astronauts return to Earth with permanent vision impairment. The condition is called space-associated neuroocular syndrome, and we still do not fully understand it. And this is in low Earth orbit. This is inside the magnetosphere. This is with regular resupply missions, with the ability to evacuate to Earth within hours if something goes catastrophically wrong, with constant communication, with mission control, with food and water and medical supplies, and the psychological reassurance that home is just below you, visible through the cupola, blue and white and beautiful. This is the easy part. The bone loss, the muscle wasting, the cardiovascular changes, the vision damage. These are what happens in the gentlest space environment humans can experience. Beyond it, beyond the magnetosphere, the picture darkens fast. Earth is wrapped in something we rarely think about. A magnetic field generated by the molten iron core of our planet. It extends tens of thousands of kilometers into space, deflecting most of the charged particles that the sun and the wider galaxy hurl at us. We owe our atmosphere to this field. We owe our biosphere to it. We owe our species to it. Without the magnetosphere, The solar wind would have stripped Earth's atmosphere away billions of years ago, the way it stripped Mars. We would be living on a sterile rock. The Earth's magnetic field is the invisible shell that allowed life to happen. It is also the invisible shell that protects every astronaut who has ever flown on a space shuttle, every cosmonaut on Mir, every crew member on the International Space Station. They are all inside the bubble. Only 24 humans have ever left it. Those 24 were the Apollo astronauts. They are the only members of our species ever to travel beyond Earth's protective magnetic envelope into the radiation environment of true deep space, and what they reported should have changed how we think about leaving the cradle forever. The flashes of light in their eyes were not a curiosity, they were a measurement. A direct sensory indication that high-energy particles were passing through their bodies at relativistic speeds. Each flash represented one cosmic ray strike, and the rate at which the astronauts experienced them depended on where they were in their mission. In the early phase, still inside the magnetosphere, the flashes were rare. As they crossed the Van Allen belts, the dense regions of trapped radiation, the rate spiked. In transinsular space, beyond Earth's magnetic protection, the flashes settled into a steady, haunting rhythm. The astronauts could not see them with their eyes open. The light from their spacecraft drowned them out. But in the dark, with their eyes closed, the cosmos showed itself. What they could not see was what those same particles were doing to the rest of their bodies. Cosmic rays do not just trigger optical flashes in the retina. They tear through every cell they encounter. They break DNA strands. They damage proteins. They create cascades of secondary particles inside the body, each one capable of causing further damage. A single high-energy particle, called a high atomic number high-energy ion, an HZE particle, can punch through dozens of cells in sequence, leaving each one wounded. Some of those cells repair themselves. Some die. Some misrepair their DNA and become potentially cancerous. The Apollo astronauts received doses of radiation during their 2-week missions that exceeded what an astronaut on the International Space Station receives in 6 months. And the Apollo missions were short. They were also conducted during a relatively quiet period of solar activity. They got lucky. If a major solar storm had hit during a lunar mission, the astronauts could have died in the spacecraft. We know this because in August of 1972, between Apollo 16 and Apollo 17, a solar particle event occurred so intense that it would have delivered a lethal radiation dose to any astronaut outside Earth's magnetosphere who was not heavily shielded. Estimates suggest the dose would have been around 4 sieverts, enough to cause acute radiation sickness and possibly death within weeks. The crews of Apollo 16 had returned in April. Apollo 17 would not launch until December. The window between them, 4 months wide, contained an event that would have killed them. NASA does not advertise this near miss. The Apollo program ended for political and budgetary reasons. But the radiation environment had quietly told a story that no one wanted to repeat. The moon is not safe, and the moon is just 3 days away. Now consider what happens when you push the distance from 3 days to 9 months, the typical transit time for a mission to Mars. The radiation exposure scales not just with time but with distance. The farther you are from the sun, the less protection you have from the sun's own magnetic field, the heliosphere, which deflects a portion of galactic cosmic rays. The deeper into the solar system you travel, the more of those rays reach you. NASA has calculated that a round-trip mission to Mars would expose astronauts to a total radiation dose somewhere between 600 millisieverts and 1,000 millisieverts. The lifetime career limit for a NASA astronaut is currently set at around 600 millisieverts depending on age and gender. A single Mars mission would consume an entire career's worth of allowed exposure. And that assumes nothing goes wrong. No solar particle events, no unusual cosmic ray bursts, no equipment failures that force the crew to spend more time exposed. The estimate is the floor, not the ceiling. The effects of that radiation are not immediate. Astronauts do not glow, they do not collapse. They do not die in their spacesuits halfway to Mars. The damage is statistical. It increases the lifetime probability of cancer. It potentially damages the central nervous system. Recent research on rodent models exposed to simulated galactic cosmic radiation has shown changes in cognitive function, mood disorders, and what some researchers have called space brain. The animals showed deficits in spatial memory, behavioral changes resembling anxiety, and physical damage to neurons in the brain regions associated with learning and emotional regulation. Whether the same effects translate fully to humans remains uncertain. We have not run the experiment because we cannot ethically run it. But the early data is worrying. Astronauts heading to Mars might not just arrive with a higher cancer risk. They might arrive with measurable cognitive impairment. They might be slightly less themselves. And the closer the mission gets to its destination, the harder it becomes to do anything about it. Because here is the part that changes everything. The farther you go, the more alone you are. Not socially alone, physically alone, causally alone. On the International Space Station, communication with Earth is essentially instantaneous. A signal travels from the station to the ground in less than 2 milliseconds. Crew members can speak with mission control as if they were on a phone call. If something goes wrong, ground engineers can troubleshoot in real time. They can talk an astronaut through repairing a piece of equipment, diagnosing a medical symptom, recovering from a software glitch. The conversation flows like any conversation on Earth. Now move the mission to the Moon. The one-way light delay becomes about 1.3 seconds. Conversations begin to feel slightly stilted. There is a pause after every question. The Apollo astronauts and Houston flight controllers developed a clipped, efficient verbal style to work around the delay. It was manageable. It was annoying, but manageable. Now move the mission to Mars. The one-way light delay ranges from about 3 minutes when Mars is closest to Earth to over 22 minutes when it is on the far side of the Sun. Round trip, that is up to 44 minutes for a single question and answer. Real-time conversation becomes impossible. Mission control becomes an advisor, not a partner. The crew is on its own. If something goes wrong on a Mars mission, the astronauts cannot call for help and receive guidance within any useful time frame. They have to know what to do, or they have to figure it out themselves, or they have to die. The Mars problem is what space agencies call communication blackouts. They are not blackouts in the literal sense. The signal does not go away. It just arrives too late to matter. And the farther you push outward, the worse this becomes. A signal from Jupiter takes about 35 to 52 minutes one way depending on orbital positions. From Saturn, more than an hour. From the Kuiper Belt, several hours. From the heliopause, where Voyager 1 currently sits, more than 22 hours. By the time you receive a message and respond, an entire Earth day has passed. The closest star, Proxima Centauri, is 4.24 light-years away. A round-trip message there and back takes 8.48 years. You could ask a question, raise a child to 2nd grade, and still not have an answer. This is not a technological problem. It is a problem with the laws of physics. The speed of light is the speed of causality. Nothing in this universe, no signal, no message, no rescue, can travel faster. And so the deeper you go, the more disconnected you become from every support system humanity has ever built. You become an island, a small, fragile, biological island, in a void that is actively trying to dismantle you. And the void does dismantle, not just through radiation, through the basic physics of being in a place that was never designed for warm, wet creatures with delicate internal chemistry. Take heat. On Earth, heat dissipates through 3 mechanisms. Conduction, where heat flows through direct contact with cooler material. Convection, where moving air or fluid carries heat away. And radiation, where heat is emitted as electromagnetic waves. In space, 2 of those 3 mechanisms barely work. There is no air to convect heat away. There is no large mass of cool material to conduct it. The only way to lose heat in space is to radiate it. And radiation is slow. Spacecraft generate enormous amounts of heat. The crew bodies generate heat. The electronics generate heat. The life support systems generate heat. The sunlight pouring onto one side of the craft heats it intensely. And all of that heat has to go somewhere, or the interior temperature climbs until equipment fails and the crew cooks. Spacecraft solve this problem with radiator panels, large flat surfaces designed to emit infrared radiation into the cold of space. The radiators have to be enormous. The International Space Station has 14 of them. They are some of the largest structures on the station. If those radiators fail, the station has hours before internal temperatures become dangerous. Move farther from the sun, and the radiator design becomes easier in some ways and harder in others. There is less sunlight to deal with, but the spacecraft electronics still generate the same waste heat. Move closer to the sun on a mission toward Mercury or beyond, and the problem inverts. You are baking. You cannot get rid of the heat fast enough. The Parker Solar Probe, currently the closest human-made object to the sun, has to hide its instruments behind a 4.5-inch carbon composite heat shield that experiences temperatures over 300 degrees Celsius, while the instruments behind it stay at around 30 degrees Celsius. The engineering required to manage that gradient is extraordinary, and Parker is not carrying humans. Humans are even more fragile than electronics in some respects. We have a survivable temperature range of perhaps 50 degrees Celsius, from coldest to hottest if we are dressed properly. The cosmos cares nothing for that range. Now think about food. On the International Space Station, food is resupplied regularly. Crews receive packages from Earth every few months. The variety is limited but adequate. Astronauts can eat fresh fruit for a few days after a resupply, then they shift to packaged meals. Their food is shelf-stable, vacuum-sealed, designed for microgravity consumption. Nothing crumbles, nothing floats away. The total mass required to feed a crew of 6 for a year is approximately 200 kilograms of food and packaging. That mass has to be launched from Earth. Every kilogram of food costs thousands of dollars to deliver to orbit. Multiply that by the duration and crew size of any mission farther than the station, and the numbers become impossible. A Mars mission with a crew of 4, lasting roughly 2.5 years, would require approximately 11,000 kilograms of food. That is just the food. It does not include the packaging, the storage containers, the preparation equipment, the water for rehydration, the disposal systems for the waste. The full food system mass for a long-duration mission is several times the food mass itself. And the longer the mission, the more food degrades. Vitamins break down, fats oxidize, carbohydrates lose their nutritional value. Astronauts on long missions experience progressive nutritional deficiencies. Even when their caloric intake is adequate, we do not yet know how to keep food fresh and nutritionally complete for a multi-year journey. We have not solved that problem. We are not close to solving it. And the prospect of growing food in space, the so-called space garden that science fiction loves to depict, runs into its own walls. Plants need light. They need water. They need nutrients. They need waste removal. They need protection from radiation, which damages plant DNA just as it damages animal DNA. They need stable gravity, which space does not provide. Experiments on the station have managed to grow small quantities of lettuce, radishes, and other simple crops. They are educational. They are inspiring. They are nowhere near sufficient to feed a crew. To grow enough food to sustain a multi-year mission, you would need a hydroponic farm of substantial size, and that farm would itself require maintenance, redundancy, and a massive investment of energy and water. Closing the loop on food production in space remains one of the unsolved problems of long-duration human spaceflight. And then there is water. Water is heavy. 1 liter of water has a mass of 1 kilogram. An adult human needs approximately 2 to 3 liters of water per day for drinking and food preparation, plus additional water for hygiene, washing, and equipment cooling. The total water requirement per astronaut per day, including all uses, is approximately 20 to 30 liters. Multiply by crew size and mission duration, and you arrive at impossible numbers, so spacecraft recycle. The International Space Station's environmental control and life support system recovers approximately 90 to 93% of the water consumed on the station. Sweat, urine, exhaled moisture, all of it is captured, filtered, purified, and returned to the drinking supply. It works. The technology has been refined over years. But it is not 100% efficient. There are always losses. And the system requires constant maintenance, regular replacement of filters and components, and a steady supply of spare parts from Earth. On a Mars mission, that supply chain becomes brittle. On a mission beyond Mars, it breaks. Send a crew to Jupiter, and a single failure of the water recycling system becomes potentially terminal. There is no resupply, there is no rescue. There is only what the crew brought with them and what they can fix with the tools they have. This is the heart of the problem. The farther you go, the more self-sufficient you must be. And the more self-sufficient you must be, the more massive and complex your spacecraft becomes. The more massive and complex your spacecraft becomes, the more fuel you need to push it. The more fuel you need, the larger the rocket required at launch. And the rocket equation, the fundamental equation governing all chemical propulsion, is unforgiving. It tells us that the mass of fuel required grows exponentially with the velocity change needed for a mission. Doubling the destination velocity does not double the fuel. It increases the fuel exponentially. To reach low Earth orbit from the surface of Earth requires a velocity change of approximately 9.4 kilometers per second. The fuel required to achieve that velocity is roughly 96% of the total launch mass of a typical rocket. Of every kilogram you stand on the launch pad, only about 4% reaches orbit. The rest is fuel and discarded stages. To reach Mars from low Earth orbit requires another 4 to 5 kilometers per second. To return from Mars to Earth requires roughly the same. To reach Jupiter and return requires substantially more. To reach Pluto and return is mathematically possible but enormously expensive in terms of mass and fuel. To reach the nearest star with chemical propulsion would require a rocket so massive that the fuel needed to lift the fuel would exceed the mass of the observable universe. The rocket equation does not care about our dreams. It does not bend for us. It is a wall. This is why every serious proposal for true interstellar travel involves either physics we do not yet have, fusion propulsion, antimatter propulsion, beam propulsion, or timescales so long that the crew would have to live and die and be replaced multiple times before reaching the destination. Voyager 1, currently the farthest human-made object in existence, is traveling at approximately 17 kilometers per second relative to the Sun. At that speed, it would take more than 73,000 years to reach Proxima Centauri if it were aimed there, which it is not. 73,000 years. Longer than the entirety of recorded human history. Longer than agriculture has existed. Longer than the species Homo sapiens has been anatomically modern. And Voyager has no crew. It has no life support. It has no need to recycle water, or grow food, or shield itself from cosmic rays for that long. It just drifts, slowly cooling, slowly running out of plutonium power, eventually going silent. The idea that humans could survive a journey of that duration is currently science fiction, not because we lack the engineering ambition, because we lack the biology. Our bodies break down on timescales much shorter than that. And the longer the journey, the more chances for something to go irreversibly wrong. And something always goes wrong. This is the lesson of every long-duration spaceflight humanity has ever conducted. Equipment fails, systems degrade, humans make mistakes, solar storms hit at the wrong moment, software glitches cascade into hardware failures. The Apollo 13 mission, which we remember as a triumph of problem-solving, was caused by a single oxygen tank malfunction. A small ignition wire inside the tank, which had been damaged during ground testing months before launch, sparked, ignited the oxygen, and blew the side off the service module. The crew lived because they were close enough to Earth to swing around the moon and use the lunar module as a lifeboat. If that same malfunction had occurred on a Mars mission, the crew would have died. There's no swing-back trajectory from interplanetary space that gets you home quickly enough to matter. The orbital mechanics of a Mars mission lock you into a roughly 2.5-year commitment. Once you leave, you are coming back when the planets align, not when you want to come back. And during that 2.5 years, the failure modes accumulate. Consider the radiation shielding question more carefully. On the International Space Station, shielding is provided primarily by the Earth's magnetic field and secondarily by the mass of the station itself. The station's walls are not thick. They do not need to be, because the magnetosphere does most of the work. Beyond the magnetosphere, shielding becomes the spacecraft's responsibility. Adding shielding means adding mass. Adding mass means more fuel. More fuel means larger rockets. There is a point at which the spacecraft becomes too massive to launch with current technology. Engineers have proposed various solutions. Water tanks lining the crew quarters, since water absorbs radiation effectively. Polyethylene shielding, which is lighter than aluminum and better at stopping high-energy particles. Magnetic shielding, which would generate a small artificial magnetosphere around the spacecraft using superconducting coils. None of these solutions has been built and tested at the scale required for a human mission to Mars. Each of them adds enormous complexity, mass, and failure modes. And each of them assumes the journey itself is the only radiation exposure to worry about, when in fact the surface of Mars also provides minimal radiation protection. The Martian atmosphere is less than 1% as dense as Earth's. Mars has no global magnetic field. Astronauts walking on the Martian surface would receive a radiation dose roughly half of what they received in transit. Not because Mars is safe, but because the planet's bulk blocks the half of the sky beneath their feet. A long stay on Mars solves nothing in radiological terms. It just shifts where the damage happens. And then there is the mind. We talk about the body as if it is the fragile thing, but the mind may be more fragile still. Humans evolved in groups. Our brains expect social contact, environmental variety, the rhythm of day and night, the smell of rain, the sight of an open horizon. None of these exist in deep space. The crew of a Mars mission would spend approximately 9 months inside a vehicle smaller than a small studio apartment with the same 3 or 4 people, eating reconstituted food, breathing recycled air, looking out a small window at a black sky that does not change. Earth, the place they came from, the place every human throughout history has called home, would shrink from a bright blue marble into a pinprick of light, indistinguishable from the surrounding stars. There is a moment on any Mars mission when an astronaut looks out the window and realizes they cannot find Earth anymore. They know it is there. They could calculate its position, but to their naked eye, it is gone, swallowed by the void. Psychologists who study isolation have begun to understand what this does to the human mind. NASA has conducted simulations on Earth, missions in which crews spend a year or more inside sealed habitats, communicating with the outside world only through delayed messages, eating only the food they brought with them, working through the same daily routines in the same enclosed spaces. The results are sobering. Crews experience what researchers call third-quarter phenomenon. Halfway through the mission, when the novelty has worn off but the end is still distant, mood plummets. Conflicts emerge. Small irritations that would be trivial in normal life become consuming. Crew members report intrusive thoughts about death, about loved ones back home, about whether the mission was worth it. Some experience hallucinations, sounds that are not there, faces glimpsed in shadows, a creeping sense that something is wrong with the air or the food or the equipment when nothing is actually wrong at all. The crews are warned to expect this. The crews are screened psychologically before they are selected. The crews are some of the most resilient humans on the planet, and they still experience these effects. Now imagine the same mission but with a one-way light delay of 22 minutes, with no possibility of evacuation. With the knowledge that even if everything goes perfectly, they will not see another human face beyond their crewmates for over 2 years. There is a phenomenon called the overview effect that astronauts who have seen Earth from space describe. The experience of seeing the planet whole, fragile, beautiful, and alone in the dark of space. It is often described as transformative, profound, spiritual. But there is no name yet for the inverse experience, the experience of looking back at Earth from somewhere so far that it has disappeared, of realizing that every human being who ever lived, every place you have ever known, every face you have ever loved is now a single faint point of light in a sky full of identical points. Some psychologists have speculated that this experience may be qualitatively different from anything humans have ever encountered. We have always been able to look up at the stars and know that we were beneath them, anchored to a known place. The astronauts of a Mars mission would be the first humans in history to look at Earth as a star, to experience their entire planet as a celestial object viewed from a distance. We do not know what that does to a person. We are about to find out. The body, meanwhile, continues to fail in ways we do not fully understand. We talked about bone loss and muscle wasting in low Earth orbit. Those problems persist on a longer journey, and they accumulate. After a 6-month rotation on the International Space Station, astronauts return to Earth weakened, Some cannot stand without assistance for hours. Many require months of physical therapy to recover their pre-flight strength. After a year on the station, the recovery time stretches to years. After 2.5 years on a Mars mission, with no centrifugal artificial gravity, with no daily exercise regimen sufficient to maintain musculoskeletal health, the astronauts arriving at Mars might be too weak to walk on its surface. Mars has about 38% of Earth's gravity. It is a fraction, but it is still gravity. A body that has spent 9 months in 0G would experience the transition to Mars gravity as a tremendous load. Standing up would be difficult. Walking would be difficult. Carrying anything would be difficult. The crews would arrive exhausted, depleted, in a state of physical compromise that no terrestrial human has ever experienced. And then they would have to perform exploration tasks on the surface of an alien world. They would have to set up habitats, drill for water, repair equipment, conduct science. In bodies that had been wasting away for the entire trip out, there is no current technology that solves this problem. Artificial gravity through rotation has been proposed for decades. It would work in principle, but building a rotating spacecraft large enough to generate one gravity at a comfortable rotation rate, without inducing nausea from the Coriolis effect, requires structures hundreds of meters across. Nothing of that scale has ever been built in space. The engineering, while not impossible, is enormous. And every meter added to the rotating habitat adds mass, which adds fuel, which adds cost, which extends the timeline. Now let us push the question further. What happens beyond Mars? What happens when we leave the inner solar system and venture into the realm of the gas giants and beyond? The first thing that changes is the Sun. From Earth, the Sun appears as a brilliant disk, half a degree across, dominating the daytime sky. From Mars, it is smaller and dimmer, about 2/3 of the brightness we see on Earth. Still recognizable as the Sun, still warm if you are unprotected. From Jupiter, the Sun is a brilliant point, only about 4% as bright as it appears from Earth. From Saturn, less than 1%. From Neptune, 0.004%. By the time you reach the Kuiper Belt, the Sun is just another star. Brighter than the others, but not by much. You could mistake it for any number of nearby stars if you did not know where to look. The Sun stops being a sun the farther you go. It becomes a memory, a landmark, a signpost pointing back to where you came from. And with the dimming of the Sun comes the dimming of solar power. Every spacecraft that has explored the outer solar system has had to confront this problem. Solar panels do not work past a certain distance. The Galileo spacecraft, which orbited Jupiter, used radioisotope thermoelectric generators rather than solar panels, because at Jupiter's distance, solar panels would have had to be the size of football fields to generate adequate power. The Juno spacecraft, currently at Jupiter, did use solar panels, but they are 3 of the largest panels ever flown on a planetary mission, each one nearly 9 meters long, deployed to capture every photon they can. Beyond Jupiter, solar power becomes impractical entirely. This is why every mission to the outer solar system has relied on plutonium. Specifically, plutonium-238, a radioactive isotope that generates heat through natural decay. That heat is converted to electricity through thermoelectric generators. The technology is reliable. It has powered Voyager 1 and 2 for over 4 decades. It powers Cassini, New Horizons, the Mars rovers Curiosity and Perseverance. But plutonium-238 is rare. The United States stopped producing it in the 1980s and only recently resumed production at small scales. The world's supply is limited. The amount available constrains how many deep space missions can be flown. And for human missions, the power requirements are much greater than for robotic probes. A human crew needs life support systems, climate control, lighting, communications, food preparation, all running continuously. Plutonium generators in current configurations would not be sufficient. You would need nuclear reactors. Real fission reactors, miniaturized for spaceflight, capable of producing tens or hundreds of kilowatts of power continuously for years. Nuclear reactors in space are not new in principle. The Soviets launched dozens of them on their ROR-SAT satellites in the 1970s and 80s. The United States flew one experimental reactor, SNAP-10A in 1965. But none of these systems were designed for crewed missions. They were small, finicky, and prone to failure. Designing a reactor that can power a crewed spacecraft to Jupiter or Saturn, that can be cooled in the vacuum of space, that can be shielded so that its own radiation does not exceed the natural cosmic ray dose, that can be maintained or repaired by a crew without specialized equipment, is one of the unsolved engineering problems of deep space travel. We can probably do it eventually. We have not done it yet. And there is another problem at the outer reaches of the solar system that nobody talks about much: cold. The temperature of deep space, far from any star, hovers around 2.7 Kelvin. That is the temperature of the cosmic microwave background, the leftover radiation from the Big Bang. Anything not actively heated will eventually cool to that temperature. A spacecraft far from the sun, with no internal heat source, would become a frozen tomb within hours of any power failure. Every fluid would freeze. Every electronic component would crack from thermal stress. Every plastic component would become brittle. The crew, if there was one, would freeze to death long before suffocation became a concern. This is why deep space missions are not just engineering exercises. They are exercises in keeping the cold out. Voyager 1 maintains its electronics at temperatures suitable for operation by using waste heat from its plutonium generator. As the generator's plutonium decays and its power output decreases, the spacecraft has to shut down more and more systems to keep critical components warm. The mission engineers know there will come a moment when the power drops below the threshold needed to maintain the heaters. At that point, Voyager will freeze. Its electronics will fail. Its transmissions will cease. The spacecraft will become a silent, frozen artifact, drifting through interstellar space forever. Current estimates suggest this will happen in the 2030s. Voyager has perhaps a decade left. And Voyager, remember, is the deepest human-made object. We have not been past it. We have not even matched it. Its journey of nearly half a century has only brought it to the edge of our own star's influence. Beyond that lies the interstellar medium proper. And what we have learned about the interstellar medium recently is that it is not the empty, quiet place we used to imagine. In 2012, Voyager 1 crossed what scientists call the heliopause, the boundary between the bubble of plasma blown outward by our sun and the surrounding interstellar gas. It was supposed to be a gentle gradient, a slow transition from solar particles to interstellar particles. Instead, Voyager hit a wall, a region of dense plasma so abrupt that scientists initially thought their instruments were malfunctioning. The density of charged particles outside the heliopause is roughly 40 times higher than inside it. Voyager went from a relatively quiet stellar wind environment to a thick soup of plasma in what amounted to a few months of travel. It was as if the spacecraft had stepped from a warm room into a freezing fog. The interstellar medium is not empty. It is denser, in many places, than the outer reaches of our own star system. The cosmic rays that pummel anything outside the heliosphere are not deflected by the sun's magnetic field anymore. They arrive at full force. Voyager's instruments recorded a spike in cosmic ray intensity at the heliopause crossing. The number of high-energy particles striking the spacecraft increased dramatically. For a human crew, that increase would translate directly into accelerated DNA damage, accelerated cancer risk, accelerated cognitive decline. The heliosphere is not just our star's bubble, it is the shield that protects everything inside it from the worst of the galaxy. Step outside, and the galaxy gets in. And we have only recently learned how much worse the picture is at certain points in the galaxy. Our solar system is moving. The Sun, with its planets in tow, orbits the center of the Milky Way at approximately 220 kilometers per second. It takes about 230 million years to complete one orbit. We have completed roughly 20 orbits since the Earth formed. During those orbits, the solar system passes through different regions of the galaxy, sometimes through dense molecular clouds, sometimes through hot ionized regions, sometimes through the spiral arms, where star formation is intense and supernovae are frequent, sometimes through relatively quiet inter-arm regions. We happen to be in a relatively quiet region right now. We are inside what astronomers call the local bubble, a region of hot, low-density gas about 1,000 light-years across, blown out by a series of supernova explosions over the past 10 or 20 million years. The local bubble is one of the safer neighborhoods in the galaxy. But it will not last. In a few thousand years, the solar system will exit the local bubble and enter a denser region of interstellar gas. The implications for any future deep space missions are not understood. The implications for life on Earth are not understood. We are passing through, and the road conditions can change. Now consider what an interstellar mission would actually face. Not a mission to Mars, not a mission to Pluto, a real interstellar mission to another star. Let us say Proxima Centauri, 4.24 light-years away, the closest stellar neighbor we have. To reach Proxima Centauri in any reasonable human timeframe, say 100 years, a spacecraft would need to travel at approximately 4% of the speed of light. That is 12,000 kilometers per second. Voyager 1 travels at 17 kilometers per second. The interstellar craft would need to be 700 times faster. The energy required to accelerate a spacecraft to that velocity is enormous. The amount of fuel required, using any form of chemical or even nuclear propulsion, exceeds what is practical. Even fusion propulsion, which we have not yet achieved, would barely scrape into the realm of feasibility. The only propulsion concepts that work at all at these velocities are beamed propulsion, where a powerful laser on Earth pushes a tiny lightweight craft, or antimatter propulsion, which requires antimatter we cannot yet produce in meaningful quantities. Suppose we solved the propulsion problem. Suppose we figured out how to get a spacecraft to 4% of light speed. The journey itself becomes a new kind of nightmare. At 4% of light speed, the spacecraft would be moving fast enough that collisions with interstellar dust grains would be devastating. A single grain of interstellar dust, smaller than a grain of sand, striking the spacecraft at that velocity, would impact with the energy of a substantial explosion. Multiple grains over a multi-year journey would shred any unshielded surface. Engineers have proposed massive ablative shields, designed to absorb impacts and gradually erode away over the journey. But every kilogram of shielding adds to the mass that needs to be accelerated. The rocket equation, again, conspires against us. And the speed itself creates other problems. The cosmic ray flux on a spacecraft moving at relativistic speeds is enhanced in the direction of travel. Particles that would have missed the spacecraft at rest now strike it because the spacecraft has plowed into them. The forward radiation environment becomes more intense. The forward shielding needs to be thicker. The mass increases further. And we have not even talked about the question of slowing down. A spacecraft accelerated to 4% of light speed has to slow down at the destination, or it will fly past Proxima Centauri in a matter of hours. Slowing down requires roughly the same amount of energy as accelerating in the first place, so the fuel requirement effectively doubles. Unless you can find a way to brake using the destination star's gravity or radiation, which is theoretically possible for very small craft, but probably not for crewed missions. The result of all this analysis is that a true crewed interstellar mission, with the current laws of physics and any conceivable extrapolation of current technology, requires either generation ships, in which the crew lives and dies and is replaced multiple times during the journey, or hibernation technology that we have not invented, or post-biological humans who can survive in forms we cannot currently imagine, or some breakthrough in physics that we have not yet made. None of these solutions is close to ready. None of these solutions has been seriously developed beyond the conceptual stage. The interstellar dream, the dream of humans walking on a planet around another star, lives in science fiction. And it remains there for reasons that are not about willpower or funding, they are about physics. The universe was not built to be traveled by warm, wet creatures with brief lifespans and large logistical needs. The universe is too big for us. The distances are too great. The forces are too hostile. The fragility of the human body is too profound. We can engineer our way into low Earth orbit. We can engineer our way to the moon. We can probably, with enormous effort, engineer our way to Mars. But each step outward is exponentially harder than the one before. And the steps after Mars become, with current physics, walls. There is a thought experiment that some space engineers like to perform. They calculate the maximum distance a human crew could realistically travel and return alive, given the most generous assumptions about technology and biology. The answer changes depending on the assumptions, but under most realistic scenarios, The answer is somewhere between Mars and the asteroid belt. Beyond that, the radiation dose becomes lethal over the mission duration. The supply requirements become impossible. The psychological burden becomes too great. The fuel requirements exceed what can be launched. The communication delays become absolute. The human body, the human mind, the human civilization that supports the mission all begin to break down. Mars is probably the limit. Not because we lack imagination, because we are made of the wrong stuff, on the wrong timescale, with the wrong needs, for a universe that is built at scales we cannot bridge. This realization is uncomfortable. It contradicts the optimism of the space age, the assumption that humanity's expansion into the cosmos is inevitable, that we are a star-faring species merely waiting for the right technology to claim our destiny. The physics suggests otherwise. The physics suggests that we are a planet-bound species, capable of brief excursions into our local neighborhood but fundamentally rooted to the world that made us. Some space advocates push back against this conclusion. They argue that breakthroughs will come, that fusion will be solved, that antimatter will become available, that we will learn to put humans into long-term hibernation, that we will engineer humans, or our descendants, into forms better suited to deep space travel. They may be right. Speculation about future breakthroughs is not the same as predicting them. The universe has surprised us before. We may be surprised again. But the patterns we are seeing now, after 70 years of spaceflight, suggest that the surprises will need to be very large indeed. In the meantime, the cost of every step outward continues to climb. Each Mars mission proposal, in real terms, costs hundreds of billions of dollars. Each requires the coordinated effort of thousands of engineers, the development of new technologies, the construction of new facilities. The investment is enormous, and the returns in terms of practical benefit to humanity are not clear. Robotic exploration costs a tiny fraction of crewed exploration and accomplishes most of the same scientific goals. The argument for sending humans is largely about the symbolic and inspirational value of human presence. That value is real, but it is also expensive, and as the targets get farther, the cost climbs faster than the symbolic returns increase. Consider what the trajectory of human spaceflight has looked like. In 1969, we landed on the moon. In 1972, we stopped. 50 years passed. We have not returned, not because we lack the capability. We have the rockets, we have the technology, we have the trained astronauts. We have not returned because the cost is enormous, and the political will has been absent. The moon, 3 days away, has been a destination we have left alone for half a century. If that is our track record with the moon, what realistic timeline applies to Mars, to Jupiter, to anywhere beyond? The Artemis program currently aims to return humans to the moon. It has been delayed multiple times. Its budget has grown, its timeline has slipped. Even if Artemis succeeds in landing humans on the moon by the end of this decade, Mars will remain at least a decade beyond that. Probably more. The Mars mission concepts currently under study would launch in the 2040s at the earliest. And those are conceptual studies. None of them is funded. None of them has hardware in development at the scale required. We are not building a Mars mission. We are studying one. The difference between the two is significant. And meanwhile, the universe continues to push back. The radiation environment is what it is. The distances are what they are. The biological limits of the human body are what they are. Each new study of the effects of long-duration spaceflight on the human body has revealed more problems, not fewer. We thought bone loss was the major issue. Then we discovered the vision changes. Then we discovered the cognitive effects of cosmic radiation. Then we discovered the cardiovascular remodeling. Then we discovered the genetic effects, the changes in gene expression after a year in space, the lingering effects months after return. Each new finding adds another constraint to what a long mission can look like. And we still do not have a complete picture. We have not run any of the long-term experiments that would give us complete data. We do not know what a 5-year zero-G exposure does to the human body. We do not know what a 3-year radiation exposure does to the human brain. We do not know how reproductive systems behave on long missions, whether children can be safely conceived or carried in deep space. whether the developing embryo can form properly without gravity. We do not know any of these things because the experiments have never been run. They cannot be run with current technology. The unknowns are not minor details. They are fundamental questions about whether humans can survive at all on the scale of mission that would be needed to reach anywhere truly far away. And the unknowns get worse the deeper we go. Imagine, for a moment, sitting in the cabin of a hypothetical interstellar craft. You are 6 months into a journey that will last decades. The sun, the actual sun that warmed every moment of your childhood, that lit every meal you ever ate on Earth, that defined the rhythm of every day of your life, is now just another star. You can see it through a window if you turn the craft properly. It is brighter than most of the others, but only a little brighter. You cannot tell which point of light it is without a star chart. The crew around you is small, maybe 4, maybe 6, the same faces every day. The same conversations every day. The same recycled air. The same recycled water. The view outside is unchanging. Stars do not move noticeably even at relativistic speeds, not when seen from inside the cabin. The destination is a faint point ahead. Home is a faint point behind. Every system in the spacecraft is critical. Any failure is potentially catastrophic. There is no rescue. There is no help. Mission Control, if it is even still operating, cannot send any meaningful guidance. Their messages take years to arrive. The mission planners who designed this voyage are dead. They have been dead for decades. You are operating on plans they made before you were born, based on assumptions they made about technology, about biology, about your own psychology. You hope they were right. You have no way to verify. You are alone. The cosmos around you is silent. It does not know you are there. It does not care. And it continues day after day to pass through your body, through your eyes, through your DNA. The flashes return at night. They were there for Apollo. They will be there for you. Each one a particle from somewhere unimaginably distant, a fragment of a dead star or a galactic event millions of years old, ending its journey in your retina. You watch them and try not to think about what they are doing to the cells they pass through. You try not to think about cancer. You try not to think about the way your bones are thinning even with exercise. You try not to think about the way your eyes are changing. You try not to think about the fact that nobody knows what you are experiencing because nobody has ever experienced it before. You are the first, and probably the last. The reality of deep space travel, when you strip away the romance, is that the universe was not made for us. It was not made against us either. It was made indifferent. Astronomical indifference is a strange thing to confront. We are used to environments that can be tamed, modified, adapted. We are not used to environments that simply do not register our presence. The lava flow on Earth burns hot, but it can be cooled. The hurricane batters the coast, but it can be tracked and avoided. The desert kills, but we can carry water and find shade. Space is not like any of these. Space does not respond to our presence. The radiation does not soften because we are afraid. The vacuum does not yield because we are clever. The cold does not retreat because we are determined. We can engineer barriers between ourselves and these forces, but the barriers are not made of nothing, they are made of mass. And mass costs energy. And energy is the one thing we cannot create from nothing. We have to launch it from Earth, every kilogram of it, fighting gravity all the way up. And once we have done that, we have to keep it. We cannot leave it behind. The barrier between the crew and the void is the entire structure of the spacecraft. Every wall, every panel, every layer of shielding, every kilogram of water and food and air. Lose any of it and the barrier fails. Lose enough of it and the crew dies. Space travel in this sense is the constant act of carrying an environment with you. And the farther you go, the more environment you have to carry, and the harder it becomes to carry enough. There is a phrase that the engineers use, mostly half-jokingly, to describe long-duration spaceflight. They call it controlled dying. The idea is that the crew is constantly fighting a slow loss, bone density falling, muscle wasting, radiation damage accumulating, vision degrading, Cognitive function shifting. The mission is a race between the destination and the body's deterioration. Whoever wins, wins. If the destination is close enough, the crew arrives in workable shape and can complete its task. If the destination is too far, the crew arrives wrecked. The line between these two outcomes is not always obvious in advance. We have not yet found it for Mars. We have not yet sent a crew that distance to discover empirically how badly they degrade. We have models, simulations, ground studies. They give us estimates. The estimates suggest Mars is at the edge. Beyond Mars, the estimates suggest the crew breaks. We do not have data for Jupiter or beyond, because we have never sent humans even close to those distances. We can guess, we can extrapolate. The extrapolations are not encouraging. And so we come back to the original question. Why does space travel get worse the farther we go? The answer is not one thing. It is everything. It is the radiation, which grows more intense beyond the heliosphere and accumulates over time. It is the communication delay, which grows linearly with distance and quickly exceeds any time frame useful for real-time response. It is the resupply problem, which becomes impossible past a certain orbital regime, forcing the crew toward total self-sufficiency that we do not know how to engineer. It is the propulsion problem, which scales exponentially with destination velocity, making each step outward orders of magnitude more expensive than the last. It is the psychological problem, which compounds with isolation and time, and the sheer alien strangeness of being so far from home that home becomes a star. It is the biological problem, the slow loss of bodily systems that did not evolve to function outside Earth. It is the cold, which threatens to freeze any spacecraft that runs out of power. It is the dust, which becomes lethal at relativistic speeds. It is the lack of options, the lack of rescue, the lack of any margin for error. It is all of these things together, multiplying and compounding, until the simple act of traveling outward becomes a kind of slow suicide. This is the part that science fiction never quite captures. The slowness of it. The grinding accumulation of small failures. The way the universe simply runs the clock down on any biological mission far enough from Earth. There is no monster waiting at the edge of the solar system. There is no alien threat. The threat is the cosmos itself, doing what it has always done, indifferent to whether we are there to experience it. And we, the small, clever apes who learned to climb out of our atmosphere, are still bringing our biology with us. The biology that evolved over 4 billion years to thrive in one specific environment, with one specific gravity, one specific atmospheric composition, one specific magnetic field, one specific star, one specific orbit, one specific moon, stabilizing our axial tilt. We brought all of that with us when we evolved. And we cannot leave it behind. We cannot become creatures of space, not yet. We are still creatures of Earth. And Earth is very small in the context of the cosmos. It is one rocky planet in the habitable zone of one ordinary star in one ordinary galaxy in a cosmos containing trillions of galaxies. Our biology is keyed to this specific place. Take us away from it, and we begin to unravel. And yet, we keep wanting to go. There is something in us, something deep, that pushes us to look outward, to climb the next mountain, to cross the next ocean, to reach the next horizon. We have looked at the moon and the planets and the stars beyond, and we have wanted them. The wanting is real. The wanting is human. But the universe does not bend to human wanting. It bends only to physics. And physics has built walls that get higher and harder the farther we try to go. So the question becomes not whether we can travel deeper into space, but at what cost? And whether the cost is one we can sustain. Whether the species can absorb the losses, the failed missions, the dead crews, the depleted budgets, the years of effort that produce a few photographs and a few rock samples and not much else. We have done it before. We did it for the moon. We could do it again for Mars. But for what lies beyond Mars, the math gets harder. And at some point, the math becomes refusal. There is a story from the spring of 1859 that very few people know about, but every electrical engineer who works on satellite hardening has memorized. On the morning of September 1st, A British astronomer named Richard Carrington was observing sunspots through his telescope. He was sketching them onto paper, as astronomers in his era did, when suddenly a brilliant kidney-shaped flash erupted from one of the sunspot groups. The flash was so bright, Carrington thought for a moment his telescope had failed, and a beam of sunlight had pierced through it directly. He had just observed the first recorded solar flare in human history. He noted the time in his journal, sketched what he had seen, and went on with his day. The flare had unleashed what astronomers now call a coronal mass ejection, an enormous bubble of charged particles flung outward from the sun at extreme speed. The bubble took about 18 hours to reach Earth, which is fast. Typical coronal mass ejections take 2 to 3 days. This one was moving so quickly that it overran the slower solar wind ahead of it. When it struck Earth's magnetic field, the consequences were extraordinary. Auroras appeared as far south as the Caribbean. People in Cuba could read newspapers by the light of the sky at midnight. Telegraph systems across Europe and North America went haywire. Telegraph operators reported sparks leaping from their equipment. Some operators were shocked unconscious. Some telegraph offices caught fire. The telegraph lines, energized by the geomagnetic storm, continued to send and receive messages even after the operators disconnected them from their batteries. The Earth itself had become a battery, powering the wires through induction from the disturbed magnetic field. The Carrington event of 1859 is the largest solar storm in modern recorded history. We were lucky. We had almost no technology to damage. There were no satellites, no power grids, no electronics, just telegraph systems, which were primitive enough to survive. If a Carrington-class event struck Earth today, the consequences would be catastrophic. Power grids across continents would fail. Transformers would burn out. Satellites in orbit would be damaged or destroyed. GPS would go down. Modern civilization, deeply dependent on electrical systems, would experience disruption on a scale we have not prepared for. Estimates of the economic damage range into the trillions of dollars. Recovery might take years. And this is the threat to Earth, where we have the magnetosphere protecting us. Outside the magnetosphere, a Carrington-class event would not damage equipment. It would kill crews. The radiation dose from a coronal mass ejection of that magnitude delivered to astronauts in interplanetary space would be acute. Not statistical. Not long-term. Immediate. The crew would experience radiation sickness within hours. Vomiting, fever, hemorrhaging. Many would die within days. Some would die within hours. There is no spacecraft currently designed that can shield an interplanetary crew against a Carrington-class event. The mass required for adequate shielding exceeds anything that can be launched. The current strategy on the rare Apollo missions and the planned Mars missions is to provide a small, heavily shielded storm shelter inside the spacecraft, into which the crew can retreat if a solar storm is detected. The shelter is typically a small section of the spacecraft surrounded by water tanks or polyethylene blocks. It is enough to survive a moderate solar event. It is probably not enough to survive a Carrington. And here is the part that should make anyone planning a long mission lose sleep. We do not know when the next Carrington event will happen. We have records of large solar storms going back several centuries. Solar storms of substantial magnitude occur on average every few decades. Carrington-class events appear to occur every century or two. A study published in 2012 estimated the probability of a Carrington-class event hitting Earth in the next decade at approximately 12%. That is 1 in 8. For a Mars mission lasting 2.5 years, the probability of encountering a major solar particle event during the mission is meaningful. The probability of encountering a Carrington-class event is lower, but non-zero. Mission planners have to design for the possibility. The crew has to prepare for it. And they have to know, in the back of their minds, that the sun might decide to kill them at any time, and there is essentially nothing they can do about it. The warning time, even with the best space weather monitoring, would be at most a few hours, maybe less. The Carrington event reached Earth in about 18 hours because of how fast it was moving. Faster events have been detected in the years since. The crew on a Mars mission would have less time than they would like to retreat to their storm shelter. And then they would have to sit in the shelter, possibly for days, breathing recycled air and listening to the proton fluxes batter the hull, hoping the shelter was thick enough. hoping the mission planners had calculated correctly. Hoping. The sun is one threat. But there are others. Consider what we learned from one specific experiment, the only one of its kind humanity has ever conducted. In 2015, NASA launched astronaut Scott Kelly to the International Space Station for a year-long mission. His identical twin brother Mark Kelly remained on Earth. The setup was scientifically extraordinary. Two genetically identical humans, separated by 400 kilometers of altitude, exposed to dramatically different environments for nearly 12 months. Researchers could measure how the body responded to long-duration spaceflight by comparing the twin in space to the twin on Earth. The results were unsettling. Scott Kelly's body changed in measurable, sometimes profound ways. His telomeres, the protective caps on the ends of his chromosomes, lengthened during the flight, which sounds positive until you understand that telomere instability is associated with cancer risk. They returned to normal length after he came home, but with abnormal patterns suggesting genetic instability. His gene expression changed dramatically. Thousands of genes shifted their activity. Some shifts returned to baseline after landing. Some did not. Months after returning, approximately 7% of his gene expression was still altered. Not because his genetic code had changed, but because the way his body was reading that code had been permanently shifted by the experience. His cognitive function showed measurable declines in some areas, particularly accuracy and processing speed, lasting months after his return. His immune system showed dysregulation. His gut microbiome had transformed during the flight and only partially recovered. His vision had degenerated. His arteries had stiffened. His blood chemistry was different in ways researchers are still parsing. And remember, this was a year on the International Space Station, inside the magnetosphere, with regular communication, regular exercise, regular psychological support, a varied crew of international colleagues, the ability to look down at Earth at any time. The most generous space environment humans can experience. And his body changed in ways we still do not fully understand. The Kelly twin study revealed something that the space agencies had suspected but had no direct evidence for. Long-duration spaceflight is not just a logistical challenge. It is a biological challenge. The human body adapts to space, but the adaptations are not always benign. Some of them may be permanent. Some of them may carry consequences that only emerge years later. Scott Kelly is still alive, still healthy by most metrics, but he has changed. He came back not quite the same man he left as. And then there is the question of medical care. On Earth, if you have appendicitis, you go to a hospital. They give you anesthesia, open you up, remove the appendix, and you recover. The procedure is routine. It saves lives every day. Now imagine appendicitis on a Mars mission, 3 months out from Earth, 6 months from any destination. There is no hospital. There is no surgeon. There is no anesthesiologist. There is no operating room. The crew has medical training but not surgical training. They have a small kit of medical supplies. They have a database of procedures and protocols. They have a delayed communication link to medical experts on Earth who will respond to questions with answers that arrive minutes or hours later. If a crew member develops appendicitis, the options are limited. Medication might delay the rupture for a while, but eventually the appendix must come out, or the patient dies of peritonitis. Surgery in microgravity on a small spacecraft, with no specialized equipment, by crew members who are not surgeons, is profoundly dangerous. It might succeed. It probably would not. Astronauts selected for long missions tend to have their appendixes preemptively removed before launch. They sometimes have their gallbladders removed. They sometimes have their wisdom teeth pulled. The selection process tries to eliminate as many sources of in-flight medical emergencies as possible. But you cannot remove every organ. You cannot prevent every illness. Cancer can develop during a mission, and cancer treatment in space is essentially impossible. Heart attack, stroke, kidney failure, severe infections, none of these can be adequately treated. The crew has to hope they do not get sick. They have to hope nobody falls and breaks a bone in a way that needs surgery. They have to hope nobody has a psychotic break or a violent reaction to medication. They have to hope nothing happens that requires medical intervention beyond what they can deliver themselves. And the probability of nothing happening over a multi-year mission is not high. The longer the mission, the more likely something goes wrong. The farther from Earth, the less help is available when it does. There is a peculiar form of risk that mission planners think about constantly. The crew is small, typically 4 to 6 people. Each member has specific skills. The pilot, the mission specialist, the medical officer, the engineer. If one crew member dies during the mission, those skills disappear from the spacecraft. The other crew members have to compensate. They may have cross-trained, but cross-training has limits. A medical officer who has been killed by a stroke cannot perform the surgery that might be needed 3 months later. A pilot who has died in his sleep from cardiac arrhythmia cannot bring the spacecraft in for landing. The mission plans for redundancy as much as it can. Multiple crew members trained in critical skills. Backup systems for backup systems. But the crew itself is the most fragile component. They cannot be redundant in the sense that hardware can be. Each one is unique. Each one carries irreplaceable knowledge and skill. And each one is mortal in an environment that does not tolerate mortality well. Mission planners have begun to ask, quietly, what happens if a crew member dies in deep space? There is no Earth burial. There is no return of remains for years, possibly never. What do the surviving crew members do with the body? The options are limited and grim. Refrigerated storage if facilities exist. External storage attached to the spacecraft. Ejection into space. Each option carries practical and psychological complications. None of them are good. The space agencies do not publicize their protocols for this scenario. The crew presumably knows them. The training presumably covers them. But the protocols exist because someone has to plan for the possibility, and the possibility is real. The Russians had a death in space once, sort of. In 1971, 3 cosmonauts aboard the Soyuz 11 capsule were killed during re-entry when a valve in their capsule opened prematurely and vented their air into the vacuum. They were not wearing pressure suits because the Soyuz was small and the suits did not fit if the crew was 3. They died in minutes, exposed to the vacuum of space at the boundary of the atmosphere. Their bodies were recovered when the capsule landed. They are the only humans ever to die in space, in the strictest definition of the word. Every other space-related fatality, including the Apollo 1 fire and the 2 space shuttle disasters, occurred within Earth's atmosphere or on the launch pad. The Soyuz 11 cosmonauts died in space, in the vacuum, surrounded by black sky and the curve of the Earth below them. The mission planners learned from that incident. Pressure suits became mandatory for crewed launches and re-entries. The valves were redesigned. The procedures were revised. We learn from disasters. We tighten the protocols. We add more safety margin. And the missions go on. But the lesson of Soyuz 11 was not just a technical one. The lesson was about how thin the line is between survival and death in space. The valve opened. The air left. The crew died. There was no recovery from that failure. There could not be. The vacuum does not care about second chances. And the deeper into space you go, the less margin you have for any failure, large or small. Every mission becomes a tightrope walk. And the tightrope gets longer the farther you travel. There is another category of threat that has only recently begun to be appreciated: dormant viruses. The human body carries dozens of viruses that have integrated themselves into our cells over the course of our lives. Herpes viruses, Epstein-Barr virus, varicella zoster, the chickenpox virus that hides in nerve cells and reactivates as shingles later in life, cytomegalovirus. Most of the time, these viruses sit quietly, suppressed by an active immune system. But spaceflight disrupts the immune system. Astronauts on long missions show measurable suppression of T-cell function. The viruses, sensing the weakening defense, begin to reactivate. NASA studies have documented increased rates of viral shedding in astronauts during spaceflight. The chickenpox virus reactivates more frequently in astronauts than in age-matched controls on Earth. The Epstein-Barr virus reactivates. Herpes simplex reactivates. Most of these reactivations do not cause severe illness, but they indicate that the body's viral controls are slipping. A long mission to Mars or beyond might see significant viral reactivations. Shingles outbreaks in space. Mononucleosis flares. Possibly novel illnesses we have not yet seen because we have not yet had crews in space long enough to develop them. The crew, immunocompromised by microgravity and radiation, exposed to their own reawakening viral passengers, with no access to a hospital, might face medical situations that look minor on Earth but become serious in flight. And there is the matter of microbes from outside the body. The International Space Station has a microbiome of its own. Surfaces have been colonized by bacteria and fungi that thrive in the closed environment. Some of these organisms have shown signs of changed behavior. Studies have documented certain bacteria becoming more virulent in space, more antibiotic resistant, more biofilm forming. The reasons are not fully understood. Microgravity may stress the cells in ways that trigger genetic changes. Radiation may accelerate mutation rates. The closed environment with limited microbial competition may allow certain strains to dominate. The consequences are not yet alarming on the station, where regular resupply and crew rotation limit how long any particular microbial population can establish itself. On a long mission to Mars, with no resupply and no rotation, the spacecraft's microbiome would evolve over years in isolation. What it would become is unclear. The crew, immunocompromised, would be exposed to whatever it became. The microbial ecosystem of a multi-year mission is one of the unsolved problems of long-duration spaceflight. And it is a problem that gets worse the longer the mission and the more isolated the spacecraft from Earth's microbial environment. This is the pattern. Every category of problem in space travel scales unfavorably with distance and duration. Radiation accumulates. Communication degrades. Resupply becomes impossible. Microbial ecosystems shift unpredictably. Psychological burden compounds. Bodies deteriorate. Equipment ages. Spare parts run out. Knowledge becomes outdated as new discoveries on Earth fail to reach the crew in any useful time. The mission is, in a deep sense, racing against entropy, and entropy always wins. The question is only whether the mission reaches its destination before entropy catches up with it. For low Earth orbit missions of a few months, entropy is manageable. For year-long missions on the station, entropy starts to bite. For multi-year missions to Mars, entropy may be more than the mission can handle, depending on how the engineering and biology shake out. For missions beyond Mars, entropy almost certainly wins. We are talking now about a fundamental limitation, not a technological one. Even if we could solve the propulsion problem and travel faster, the duration would not necessarily shrink, because faster travel requires more fuel and more shielding and more system complexity, which means more things to fail. There is a sweet spot somewhere, a mission profile that balances speed against complexity and reaches the optimal compromise. For Mars, we have not found that sweet spot. For destinations beyond Mars, the sweet spot may not exist within the bounds of human biology. And we have not even talked about coming back. Every mission narrative we tell ourselves emphasizes the outbound journey, the arrival, the exploration. The return journey gets less attention because it is often presented as the same problem in reverse. It is not. The return journey is, in many ways, harder than the outbound journey. The crew is more depleted, the equipment is more degraded, the supplies are more depleted. The motivation is different, because the mission has been mostly accomplished and the crew now just wants to get home. Psychologically, the return journey is often when problems peak. The third quarter phenomenon discussed earlier is amplified on the return leg. The crew, having spent months or years working toward a goal, now spends months or years just enduring. The Mars mission profile, in particular, has a brutal return journey. The crew, after spending many months on the Martian surface, would have to launch back into orbit, rendezvous with their return vehicle, and begin the long coast home. They would be weaker than when they arrived. Their bones would have continued to deteriorate even in Mars gravity. Their muscles would have wasted further. Their radiation dose would have accumulated. And the return trip, taking another 9 months or so, would deepen all of these problems. By the time they reached Earth, the crew would be in worse shape than any human has ever been after a space mission. Their re-entry would be physically traumatic. Their recovery would take years. Some of them might not fully recover. The Mars program, if it is ever flown, will produce astronauts who emerge from the experience as different people, biologically and psychologically. Some of them will write books. Some of them will retreat from public life. Some of them will struggle with the aftermath in ways we cannot predict, because no human has ever been through what they will go through. This is the part of the story that the cheerful animations of future Mars colonies never depict: the recovery wards on Earth. The astronauts learning to walk again. The astronauts being monitored for cancer for the rest of their lives. The astronauts who developed cognitive problems in flight and have to retire early. The astronauts whose marriages did not survive the years of separation. The astronauts who came back to a world that had moved on without them, where their children had grown up while they were gone, where the technology had advanced and the culture had shifted and they did not quite fit anymore. We do not talk about these things much. They do not fit the heroic narrative. But they will be real, and they will affect everyone who goes. And the deeper into space the missions go, the more profound these effects will be. For interstellar travel, the homecoming would be more profound still. A crew returning from Proxima Centauri after a century of relativistic flight would arrive on an Earth that had changed beyond their recognition. Their families would be long dead. Their training would be obsolete. Their language might no longer be spoken in its original form. The technology they understood would be primitive curiosities. The culture they remembered would be ancient history. They would be foreigners in their own homeland. And the deeper they went, the more pronounced this displacement would become. A round trip to a star 10 light-years away, even at relativistic speeds, means decades of Earth time have passed during the journey. The crew returns to a world that has lived through wars and elections and inventions and pandemics that they only know about as historical entries in a database. They have become artifacts. This is the cost of deep space. It is not just radiation and isolation. It is the slow detachment from everything that defined the crew before they left. They become creatures of the mission, of the spacecraft, of the void. And when they come back, if they come back, they have to relearn how to be human in a society that no longer exactly matches what they remember. The Apollo astronauts experienced this on a small scale. Many of them struggled after their missions. Buzz Aldrin wrote openly about his depression and alcoholism after walking on the moon. Other astronauts retreated into religion or business or quiet lives, trying to make sense of what they had done. The experience of going somewhere extraordinary and coming back is not psychologically neutral. It changes the people who do it. And the more extraordinary the trip, the more profound the change. We do not have good metrics for measuring these psychological costs. We do not select astronauts for their ability to integrate transformative experiences back into a normal life. We select them for their ability to perform under pressure during the mission. What happens after, we leave to them to figure out. The deeper missions go, the more we are asking individuals to bear costs that society does not fully acknowledge. Now let us pull back and ask the broader question. If space travel gets worse the farther we go, in so many compounding ways, what does that mean for humanity's future in space? The answer, when you face it honestly, is complicated. It does not mean we should stop. The robotic missions have been spectacularly successful. They have taught us more about the universe than any other scientific enterprise in history. Voyager, Cassini, the Mars rovers, the James Webb Space Telescope. These instruments have rewritten our understanding of the cosmos. And they continue to do so. The case for robotic exploration is overwhelming. It is cheap relative to crewed missions, it is safe relative to crewed missions, and it can accomplish almost all of the scientific objectives that crewed missions could accomplish. For the foreseeable future, robotic exploration will be how humanity engages with the deep cosmos. We will see Jupiter and Saturn and Neptune through robotic eyes. We will land on Europa and Titan and Triton with robotic probes. We will eventually fly through the outer reaches of the heliosphere and into the interstellar medium with robotic ambassadors. None of this requires us to put human bodies through the trial of deep space travel. The crewed missions, when they happen, will be limited. Mars is the realistic horizon. The moon is the practical destination for now. Permanent crewed bases on the moon may be feasible in the coming decades, supplied regularly from Earth, providing a platform for science and for staging deeper exploration. A Mars mission, when it flies, will be a national or international project of decades-long scale and trillions of dollars in cost. It will probably happen, eventually, because the human drive to go is real and persistent. But it will be hard. Crews will struggle. Some may die. The mission will probably produce profound results, both scientifically and culturally. And then we will look beyond Mars and find that the cost of going further is too high. The next great leap, the leap to other stars, will likely wait for capabilities we do not yet have. Fusion propulsion, if it can be realized at scale. Some form of long-term human hibernation, if it can be developed. Post-biological forms, if humanity ever takes that path. None of these are imminent. None of these are guaranteed. In the meantime, the cosmos waits. It is not going anywhere. The stars will still be there in 1,000 years, in 10,000 years, in 1,000,000 years. If our species survives long enough, if our civilization endures long enough, if our descendants are interested in reaching them, the technology may eventually exist. The first interstellar mission may launch 1,000 years from now, crewed by people whose ancestors we cannot imagine, using physics we have not yet discovered, on a mission that takes lifetimes to complete. Or it may never launch at all. The universe is patient with our impatience. It tolerates our dreams without nurturing them. The walls between the stars are real, and they were built by physics, and physics does not negotiate. There is a meditation that some space scientists return to when they think about all of this. The fact that we are, ourselves, made of stardust. That every atom of carbon in our bodies, every atom of oxygen, every atom of iron, was forged inside stars that died billions of years ago. We are not separate from the cosmos. We are the cosmos. We are arrangements of matter that the universe has produced, over 14 billion years, capable of looking outward and asking questions. From a certain angle, the inability to travel between stars is not a tragedy. We do not have to travel between stars to be cosmic. We already are. The journey we take, from a quantum fluctuation in the early universe, through stellar nucleosynthesis, through chemical evolution, through biological complexity, to consciousness, is already an interstellar journey of the most profound kind. Our atoms have come from very far away. Our DNA contains the chemistry of supernovae. When we look up at the stars, we are recognizing kin. We do not need to physically visit other star systems to be connected to them. We are connected to them by lineage. This is what some scientists tell themselves when they confront the limits of space travel. It is not entirely consolation. It does not replace the dream of walking on a planet around another star. But it is something. It is a way of holding the disappointment without despair. The universe is too big for us to traverse in bodies, but the universe is also small enough to fit inside us, in a sense, through our understanding and our connection to its history. We are the universe's eyes briefly opened. The fact that we cannot reach all of it does not diminish the looking. The looking itself is significant. The asking of the question is significant. The patient, careful work of measuring and modeling and understanding is significant. Even if we never set foot on another star's planet, we have already mapped them with instruments that probe the atmospheres of worlds light years away. We have already detected the chemical signatures of water and methane and carbon dioxide in those atmospheres. We have already taken pictures of planets around other stars, faint dots beside their host stars but real, photons that traveled across light years to land on our detectors. We have already done astonishing things from our cradle. We have reached out across distances we cannot physically traverse and learned things about them. That is its own form of travel, of a sort. It is not the same as going, but it is not nothing. And yet, the longing remains. The pull outward is built into us. Whether by evolution or by something more elusive, we are the species that climbs and crosses and explores. The deep history of human migration spans every continent on Earth. We did not stop at any horizon. We kept going until the entire planet was inhabited. Space is the next horizon, the natural horizon. We have already crossed the lower thresholds. We have orbited. We have landed on the moon. We have sent our machines to every planet in the solar system. The next step is Mars. The step after Mars is harder. The step after that may be unreachable in any meaningful sense for our biology. But we are still going to try. Some fraction of every generation will be drawn to the dream. Some fraction will dedicate their lives to making the next step possible. And some fraction of them, the smallest fraction, the most committed and most fortunate, will actually go. They will leave Earth. They will travel out into the void. They will become, briefly, parts of the cosmos that the cosmos can experience directly. And then they will come back, if they come back, changed forever, carrying with them stories and data and the slow accumulation of damage that the universe inflicted on their bodies during the trip. The story of space travel is not just a story of progress, it is also a story of cost. Every kilometer outward is paid for in radiation and isolation and biological wear. Every step requires another decade of engineering and another generation of crews willing to accept the risks. The optimistic timelines you see in the press, the prospect of Mars cities by 2040, or interstellar travel within a century, do not survive careful examination of the obstacles. The pessimistic timelines in which humans never leave Earth's neighborhood permanently are also probably wrong. The truth lies somewhere in between, in a future where some humans go to Mars, some humans build moon bases, some humans live in orbit for years at a stretch, and the rest of humanity stays home and watches and reads the reports. The truth is a future in which space exploration continues but does not become routine, in which the cosmos remains a place we visit briefly rather than a place we inhabit, in which the dream of a multiplanetary species is partially realized but never fully completed in the form that science fiction imagined. This is not a failure. This is what is actually possible, given the physics we live with and the bodies we have. But the question that hovers over all of this, the question that returns again and again, is what becomes of us if we ever truly do leave? If we ever truly do build the spacecraft that can take a crew between stars? If we ever truly do develop the biology that can survive the journey? What kind of beings do we become at the end of that process? Are they still human in any recognizable sense? Are they our descendants in any meaningful way? Or have they been so transformed by the requirements of space, biologically and culturally, that they have become something new, something separate from the species that launched them? This is not idle speculation. The pressures of long-duration space travel will reshape any species that subjects itself to them. The crews who go far will not be the crews who came back, even biologically. And if a generation ship ever launches, the crew that arrives at the destination will not be the crew that left. They will be the descendants of that crew, born and raised in the spacecraft, knowing only the spacecraft as their world. They will have evolved or been engineered for the environment of the ship. Their relationship to Earth will be theoretical. They will not have walked on a planet. They will not have felt rain. They will not have known any sky other than the painted ceiling of their habitat. When they arrive at the destination, if they ever arrive, they will be a different people from the one that sent them. The connection between origin and destination will be tenuous. The species that launches the ship and the species that arrives at the destination star will share genetics but very little else. And if this is the long-term future of human space travel, the future of generation ships and slow voyages and transformed descendants, then the universe is in a sense already lost to us in our current form. The walking, talking humans who watch documentaries and dream about going to the stars are not the ones who will get there. The ones who will get there, if any do, will be our descendants reshaped by the demands of the cosmos. We are the ancestors. They are the strangers we are sending forward into the dark. We can wish them well. We can build the foundations of their voyage. But we cannot ourselves go. The cosmos is not for us. It is for whoever we become. But there is another way to think about all of this, and it is the way that comes back to me again and again when I sit with these problems late at night. The walls that physics has built between us and the rest of the cosmos may also be a kind of gift. They force us to pay attention to what we have. They make every photograph from a distant world more precious. They make every successful mission an act of triumph rather than routine. They make the brief glimpses we get of other worlds, through the eyes of robots we have built and sent ahead, into something close to sacred. We do not get to take the cosmos for granted. We cannot. The cosmos will not let us. Every step we manage to take outward is an achievement against the indifference of the universe, and the achievements are meaningful precisely because they are hard. Imagine if space travel were easy. Imagine if we could pop over to Mars for a long weekend, or take an annual vacation to the moons of Jupiter, or send our children on summer trips to the rings of Saturn. The cosmos would shrink, the mystery would fade, the wonder would become familiar, and familiarity has a way of dulling everything it touches. The fact that the cosmos resists us, that it does not yield to our desires, that it makes us work for every kilometer of progress, is part of what keeps it numinous. The difficulty is part of the value. This is not a consolation prize. It is a real reframing. The species that masters its solar neighborhood without ever leaving it, that builds telescopes capable of resolving the atmospheres of planets around distant stars, that uses spectroscopy to detect water and oxygen and possibly biosignatures on worlds we will never visit, that maps the cosmic web and the dark matter halos and the structure of the universe across billions of light years, all from this small rocky planet, is doing something extraordinary. The mind reaches farther than the body. The mind always has. From the moment a human first understood that the stars were other suns, the human mind was traveling among them. The instruments are extensions of the mind. The data they bring back is a form of arrival. We have already arrived at every star we have studied. We have arrived in the way that matters most. We have looked at them, understood them, fit them into a story we are telling about the cosmos. The physical journey is one form of travel. The cognitive journey is another. And the cognitive journey, in many ways, is the deeper one. The robots that we send into the cosmos are, in a sense, our advance party. They are not us, but they are extensions of us. They carry our questions, they carry our cameras and our spectrometers and our instruments of inquiry. They are designed by us, built by us, programmed by us, monitored by us. When the Curiosity rover takes a panoramic image of the Martian landscape and beams it back to Earth, every photon of that image has been seen by human eyes within hours of arrival. The information travels at the speed of light. The understanding travels with it. The rover is, functionally, an extension of the engineers and scientists who built it. They are not on Mars, but their attention is. Their inquiry is. Their interest is. The robot is the body. The mission team is the mind. Together, they are a form of human presence on another world. This is not the same as having a crew on the surface. It is not as romantic, it is not as dramatic. But it is real, and it is far cheaper, and it costs no bones and no eyesight and no cognitive function. The robots can stay on Mars for years. They can spend their entire operational lifetime in the harshest environments without complaint. They do not need food, water, air, or sleep. They are perfect for the work. The crew, if it ever flies, will be there for prestige and inspiration. The robots are there for science. And the robots are improving. The Mars rovers of today are far more capable than the rovers of 20 years ago. They drive farther, drill deeper, analyze more samples, transmit more data. The next generation will be smarter still, capable of more autonomous decision-making, less reliant on the long delays of Earth-based commanding. Eventually, we will have robots that can survey entire planets in detail, sample their atmospheres and surfaces and subsurfaces, characterize their chemistry and biology if any biology is present. We will have robots on the moons of Jupiter, drilling through ice into oceans that have been hidden from sunlight for billions of years. We will have robots on Titan, sailing the methane seas. We will have robots on Pluto, mapping its strange geology in finer detail than we currently map remote regions of our own planet. None of this requires a single human to leave Earth. The exploration of the solar system, in its most thorough form, is achievable by robots, and the cost is a fraction of what crude exploration would cost. The science is essentially the same. The only thing the robots cannot do is have the experience of being there. The experience is left for us to imagine, guided by the data they send back. We have to do the imagining ourselves. But humans are good at imagining. We have been doing it for as long as we have been a species. The cosmos has always been mostly imagined. Even now, looking up at the stars with your naked eye, you are mostly imagining what you are seeing. The actual photons are sparse. The understanding is built in your mind. For the deeper cosmos, beyond the solar system, telescopes are our agents. They are not as tangible as the rovers. They do not have wheels or robotic arms, but they collect light from impossibly distant sources, and that light tells us nearly everything we know about the universe beyond our local neighborhood. The James Webb Space Telescope, which we discussed in earlier journeys, has rewritten our understanding of the early universe. Galaxies that should not exist according to our models are appearing in its images. The cosmic web is being mapped in greater detail. Exoplanet atmospheres are being analyzed for the chemical signatures of life. None of this requires us to travel anywhere. The light comes to us. The cosmos sends its messages in photons. and the photons arrive at our detectors, and we read them. This is also a form of travel, of a kind. The light that left a galaxy 13 billion years ago has finally arrived at Earth, and it has been collected by an instrument we built and launched, and the information encoded in that light has become part of our understanding. The galaxy and we have met in a sense. The meeting did not require us to move, it required the universe to send us a message, and us to be ready to receive it. We have made ourselves ready. We have built the instruments. We have refined our understanding to the point where we can interpret what the light is telling us. The meeting is real, even if no body has traveled. This is a different model of exploration than the science fiction model. It is not crews of humans walking on alien shores. It is a network of instruments, both robotic and remote sensing, gathering information from places we cannot physically reach. It is humanity becoming, in a sense, a planetary mind, with sensors distributed across the solar system and gazing out at the rest of the universe. We are not multiplanetary in the sense that we live on multiple planets. We are multiplanetary in the sense that we have presence on multiple planets. Through our instruments, through our knowledge, through our interpretation. The line between these two definitions of multiplanetary is one that we may need to start blurring. The future of human engagement with the cosmos may be less about bodies and more about minds. Less about journeys and more about presence. Less about colonization and more about communion. And there will still be journeys. There will be a Mars mission eventually. There will be a moon base. There will be longer stays in orbit. The crewed missions will continue, even as the robotic missions go farther and do more. The crewed missions matter not because they do something the robots cannot do, but because they do something the human soul needs. We need to send some of our own. We need representatives. We need to know that humans have been there, even if those humans return with damaged bodies and altered minds and stories that the rest of us can only partially understand. The crewed missions are symbolic, but symbolism is not nothing. Symbolism is how humans make meaning. The first human footprint on Mars will be a moment that resonates through the species in ways that no robotic mission ever could, no matter how scientifically productive. The first human to look down at Mars from orbit, the first human to walk on its red sand, the first human to set up a habitat and live on its surface for a season, these will be milestones in the deep history of our species. They will be costly, they will be dangerous, they will be hard, but they will happen. Eventually, because we cannot quite let them not happen. The pull is too strong. What will not happen, almost certainly, is the fantasy version of space travel that fiction has trained us to expect. There will be no warp drives. There will be no faster-than-light communication. There will be no easy hops between star systems. The universe is too big, and the physics too restrictive for that kind of cosmos to be ours. We are going to have to make peace with the universe we actually have, the one where light is the fastest thing and stars are far apart and the human body is fragile. Making peace with that universe is not surrender, it is maturity, it is the species growing up and recognizing the actual shape of the world it inhabits. The world is not the one we wished for, not the one our stories trained us to expect, but it is the one we have, and there is enormous beauty in it, even with its limits. Especially with its limits. The cosmos rewards close attention. The closer you look, the more remarkable it becomes. The galaxies we cannot visit are still extraordinary objects to study. The stars we cannot reach are still magnificent furnaces of nuclear fusion that have been burning for billions of years. The exoplanets we cannot land on are still other worlds, real and present and worthy of our wonder. We do not need to physically arrive to engage with them. Engagement is a state of mind, not a state of location. The mind can engage from anywhere. This is, in the end, the lesson of deep space. Not that we are trapped on Earth, although in a sense we are. Not that the cosmos is hostile, although in a sense it is. The lesson is that the meaning of being in the cosmos is not contained in physical travel. The meaning is in the relationship. We are in relationship with the universe whether or not we can move through it. We are in relationship because we look at it, study it, model it, dream about it. The relationship is real even when we are stationary. The relationship was real for our ancestors who looked at the night sky from caves and named the constellations and told stories about the lights they could not understand. The relationship will be real for our descendants, whether or not they ever board a spacecraft. The cosmos has been the backdrop of human consciousness for as long as there has been human consciousness. And consciousness, in some real sense, is what the cosmos has been building toward, or stumbling toward, or accidentally generating throughout its history. We are a way for the cosmos to know itself. The fact that the body containing this consciousness cannot easily travel is less important than the fact that the consciousness exists at all. Carl Sagan said something close to this once, in different words. He spoke of us as the universe's way of comprehending itself. He spoke of the privilege of living in a moment when the universe has produced beings capable of understanding their own origins. We have inherited that privilege. We are doing the comprehending. We are the universe's eyes briefly open. Whether or not we ever physically reach other stars is, in this framing, a secondary question. The primary question is whether we use the comprehension we have, whether we look carefully, whether we ask good questions, whether we build the instruments and do the math and tell the truth about what we find, whether we honor the cosmos by paying attention to it, even when paying attention reveals things we did not want to find. The cosmos has revealed plenty of things we did not want to find. It has revealed that we are small, that our planet is unremarkable, that our star is ordinary, that our galaxy is one of trillions, that the laws of physics do not bend for our preferences. It has revealed that space travel is hard and gets harder the farther we go. None of this is what we hoped for. But it is the truth. And the truth, even when it is uncomfortable, is what we have been built to seek. And the seeking continues. The next generation of telescopes is already in design. The next generation of spacecraft is already being built. The next generation of mission planners is already in graduate school, working through the problems that will define their careers. Some of those people will solve problems that we currently consider unsolvable. Some of those problems will turn out to be harder than we thought. Some breakthroughs will happen. Some will not. The work continues, generation after generation, with no guarantee of the outcome. This is what science is. This is what exploration is. It is the long, patient labor of pressing against the boundaries of the possible and seeing where they yield and where they do not. The cosmos may yield more than we currently think. The body may turn out to be more adaptable than we currently know. The physics may have loopholes we have not yet found, or it may not. Either way, the work is the point. The work is the relationship. The work is how we engage with the universe that produced us. In the small hours of the morning, when I think about the astronauts who have died on missions and the astronauts who will die on future missions, I come back to the flashes of light in their eyes. The cosmic rays passing through their retinas, leaving trails of damage too small to feel but real enough to record as bright streaks against the dark of closed eyelids. The astronauts watched the cosmos pierce them and they kept going. They knew the cost. They went anyway. They went because something in them needed to go, and they went on behalf of all of us, the ones who stayed behind. The Apollo astronauts brought back rocks from the moon and stories about flashes in their eyes and a perspective on Earth that has never quite left our culture. They paid for that perspective with their bodies, with the years of training, with the lifetime monitoring for cancer and cognitive change, with the strange quiet displacement that came over many of them after they returned. The price was high. The benefit was real. The trade was made. And the trade has continued to be made in smaller ways by every astronaut since. Every long-duration crew member on the International Space Station, every cosmonaut on Mir, every crew that has flown the Soyuz, the shuttle, the various capsules and habitats, they have all paid something. They have all brought something back. The future astronauts who go to Mars will pay more. They will lose more bone, more muscle, more vision. They will absorb more radiation. They will spend longer in the strange psychological territory of being unreachable by anyone who cares about them. They will come back, if they come back, as different people, and the trade will again be made, and the benefit will again be real, and the next generation of humans will know that humans have walked on Mars. The knowing will matter. It will not feed anyone. It will not cure any disease. It will not directly improve life on Earth. But it will be a fact that humans walked on another planet. And that fact will live in the species' memory, the way the moon landing lives in our memory now. A touchstone, a reference point, a proof that we did the thing that was once impossible. We will need such proofs. We will keep needing them. Every generation will look back at the previous one and ask, what did you do? And the answer sometimes will be, we went farther. The going farther is not pragmatic. It is not necessary, but it is part of who we are, and it appears that we are not capable of being the species that does not go. The species that does not go is a different species. It is not better or worse, it is just different. There may be such species elsewhere in the cosmos, contented intelligences that achieve their full potential on their home planets and never feel the pull outward. They may be common, they may be the norm. The pull outward may be unusual, may be a quirk of evolution, may be a feature of certain primate brains, in particular environmental conditions. We do not know. We only know our own pull, and our own pull is real. And so we will go. We will keep going, as far as our bodies and our budgets allow, and probably a little further than is wise. And we will leave a trail of small triumphs and small disasters and small data sets behind us. And eventually, after a long while, the going outward will become more reasonable. The technology will improve. The biology may be augmented. Some descendants of ours may inherit the cosmos in ways we cannot. Or they may not. We cannot see that far ahead. But we can see this. We can see ourselves here, now, in this particular moment in cosmic history, looking outward with the best tools we have ever built, asking the deepest questions we have ever asked, and pushing carefully against the walls that physics has set between us and the rest of everything. The walls are real. We have spent these hours together exploring them. The radiation, the distance, the cold, the supply requirements, the propulsion limits, the biological fragility, the psychological burden, the communication delays, the failure modes that accumulate over time. All of it is real. All of it makes deep space travel harder the farther we try to go. But the walls are not a verdict on our worth as a species. They are a feature of the cosmos. They were here before us. They will be here after us. They define the playing field within which we live. And within that playing field, there is still enormous room for wonder, for inquiry, for exploration, for growth. We have not exhausted our own solar system. We have not exhausted the questions about our own planet. We have not exhausted the science of our own bodies. We have endless work to do without ever leaving our cradle. And the work we do here, on Earth and in low orbit and on the Moon and eventually on Mars, will determine what we know and who we become for generations. The cosmos is not a vacation destination. It is not a frontier waiting to be claimed. It is the larger context in which our small lives unfold. It is the air we breathe, conceptually. It is the backdrop against which we measure ourselves. And it is enough in its vastness and its difficulty and its beauty to occupy our attention for as long as our species exists. We do not have to reach every star to be cosmic beings. We are already cosmic beings, made of star matter, conscious in the universe that produced us, capable of asking questions and finding answers about phenomena that occurred billions of years ago in places billions of light years away. The cosmos has, in producing us, granted itself a witness. The witness does not have to travel everywhere to be a witness. The witness only has to look and listen and think carefully and report what it finds. We have been reporting for thousands of years. We will keep reporting for as long as we last. And the cosmos, indifferent and patient and unimaginably old, will keep providing material for the reports as long as we are willing to attend to it. So when you next look up at the night sky, on a clear night away from city lights, and you see the thousands of stars scattered across the dark, remember what we have explored tonight. Remember that those stars are far. Remember that the cosmos between you and them is filled with forces that would kill any unprotected body. Remember that the journey to even the nearest of them is, with current physics, a journey of generations. Remember the cosmic ray flashes that Apollo astronauts watched in the silence of their journey to the moon. Remember that going farther means accepting more of those flashes, more of the slow damage, more of the silence. Remember that we have not figured out how to make the journey safe. Remember that we may never figure it out. And then remember that we have, despite all of this, looked at those stars, and learned their distances and their temperatures and their chemical compositions and their histories. We have done extraordinary things from this small planet. We will keep doing them. The looking will continue, the asking will continue. The slow, patient work of understanding will continue. And in the looking and the asking and the understanding, we will be in relationship with a cosmos that is too large for us to traverse but not too large for us to know. Knowledge is a form of arrival. We have already arrived in a deep sense at almost everywhere we have ever looked. If you enjoyed this journey through the realities of space travel and what they mean for our species, please take a moment to like this video and subscribe to Hidden Beyond Stars. It helps us continue making these long-form explorations of the cosmos and our place in it. Tell me in the comments what surprised you most about the obstacles to deep space travel. Tell me whether you think humanity will eventually overcome them, or whether you think we will, in the end, remain a planet-bound species exploring the cosmos through our instruments rather than our bodies. There is no wrong answer to that question. We do not yet know what the future holds. But we can imagine, we can discuss, we can hold the possibilities in our minds and turn them over and see what we make of them. That is part of what these journeys are for. They are not just information. They are invitations to think, to wonder, to sit with the largeness of the cosmos and our smallness within it, and find a way to be at peace with both. The astronauts of Apollo 11 saw flashes of light in their eyes during the long coast to the moon. Those flashes were cosmic rays from supernova explosions millions of light years away, particles that had been traveling through space for an unimaginable time before finding their way into the retinas of 3 men in a small spacecraft. The men did not stop them. The men could not stop them. The men simply experienced the cosmos passing through them, briefly, on their way to somewhere very near home by cosmic standards. The flashes have been there for every astronaut since. They will be there for every astronaut to come. They are the universe announcing itself, particle by particle, in the silence of space. The deeper we go, the more of them we see. The more of them we see, the more we understand that we have not really left at all. The cosmos was always here. It is here now. It is passing through you, right now, as you sit in your room and listen to this voice. The cosmic rays are striking your body. They are striking your DNA. They are part of what defines you, biologically. You have never been separate from the universe. You have never needed to travel to it. It is already inside you, and it is already around you, and it is already what you are made of. The walls between you and the deepest reaches of space are real, but they are not as separating as they might seem. The cosmos finds its way to us. It always has. And in the brief flicker of consciousness that is our species' moment in this universe, we look up and we see the light from very far away, and we understand, a little, what it means. That understanding is the journey. That understanding is the destination. That understanding is what we are here for. Look up tonight. The cosmos is waiting. It has been waiting for billions of years. And it will keep waiting, patient and vast and beautiful, long after we are gone.